Hi everyone, welcome back to another Mathline video. Today we're doing 7.1, which is inductive reasoning to find a specific term. Basically, to simplify what this is, it's just us noticing patterns in specific examples and then using that to draw conclusions from them. In science, we would call that experimental method, and in math, we call that inductive reasoning. So there's an example of comparing that to science, but inductive reasoning is actually something we see in all areas of life. We could use inductive reasoning even with human behavior. So for socialization, we could look at patterns of behavior that you see going on in one group or in one area, and then we could use that to then make predictions based on that. So let's take a look at some mathematical examples of this. Let's take a look at the patterns of multiplying these numbers. So if we have 1 times 1, you already know this, the answer is 1. You already know this one too. 11 times 11 is 121. But notice how I've written them out to sort of get your eye to draw your attention to some of the patterns that are going on. The next one you probably didn't know. 111 times 111 has this answer, 12,321, but notice the pattern of what's going on here. It goes 1, 2, 3, and then it goes down to 2 and 1. So 1, 2, 3, 2, 1. So basically, the numbers are approaching 3 from either side in ascending order from the left, so getting larger, and then descending order going towards the right. 3, 2, 1 here. So, and then the other pattern that I'm hoping that you're noticing when you look at this is if you take a look at the number of digits that we have, so we have 2 1s there and times 2 1s here, and then you have a 2 in the middle. You have 3 1s times 3 1s, and you have a 3 in the middle here. So based on that, we would probably predict or think that in the middle here, we would have 4 1s here times 4 1s here, so there's probably a 4 in the middle. And then going back to that other pattern we were talking about, here it goes 1, 2, 3, so chances are that this is going to go 1, 2, 3, 4. And then here it goes 3, 2, 1, so this is probably 4, 3, 2, 1. And if you're unsure, take your calculator, punch this in, and you will find that this, in fact, is the solution that you get. So basically what this is instead of having to sit there and do 1,111 times 1,111, you can look at and notice patterns and use that to take a shortcut to make things easier. Basically, math is taking shortcuts. So using the same idea, here we have 5 1s times 5 1s, so we know there's going to be a 5 in the middle. And then we can go 1, 2, 3, 4, 4, 3, 2, 1, and we're done. So you see the advantage of noticing patterns. This is like evolution in action. If you notice, like that's what happened in math. You figure out smarter, more efficient, quicker ways of doing things so that you can just skip all the work and you can jump to the solution without doing the tedious little calculations. So that's an example of how this shows up. On to the next one. I want you to take a look at this, pause your video, and see if you can notice the pattern and fill in the blanks based on that. And when you're ready, unpause it so that you can see me going through the solution with you. So similar to last time, let's draw our attention to the pattern. 6 times 7 equals 42. You knew that. 66 times 67, you probably didn't know this, but it's 4,422. But notice that if it's 66 times 67, there's 2 6s and there's the 2 4s in the answer and the 2 2s in the answer. Here you have 3 6s times 667, and there's 3 4s in the answer and 3 2s in the answer. So based on that pattern, if there's 4 6s, it's probably 4 4s and 4 2s. And if you're unsure, take out your calculator. You can punch it in on your calculator, and you will find that that is, in fact, the answer. And here we have 5 6s, so it's probably going to be 1, 2, 3, 4, 5 4s, and times the same number but up 1 digit. So you're going to have 5 2s as well. Hardest part is writing them and fitting them all in here. So I hope that that helps and shows and clearly demonstrates to you some of the interesting patterns that come up when we're dealing with numbers like this. So the thing is, it's not all numbers, it's only some of them that show these types of patterns, and we can use that to skip steps and take shortcuts in order to find quicker, more efficient ways of doing things, which is what math is, which is also what evolution is. Okay, so on to the next one. Find the next two numbers based on the pattern that you see here. So take a look at this and let's come up with, or let's maybe first start just by noticing or talking about what the pattern is. So what we notice here is this. Again, I would say pause your video and try it on your own, and when you're ready, come back to this solution. So here we notice this is multiplied by 2. And then here I notice that that doesn't follow the same pattern. That multiplied by 2, 6 multiplied by 2 doesn't give me 8. But I do notice that I can add 2 here. And then this gets multiplied by 2, just like in the last one. And I notice that's happening here as well. So based on that, I have an idea of what the next one is probably going to be here. If I just multiply this by 2, I would just do 38 times 2, and I'd get 76 there. So then this pattern at the bottom still happens. There to there is plus 2. There to there is plus 2. So based on that, I would think that's probably plus 2 as well. So the next one here would actually be 78. So this is a little bit different than the patterns we looked at in chapter 4 in that it's not going up by the same amount each time, which is what we did when we did linear equations. It was plus 2 each time or plus 5 each time, so it was easier for us to come up with the pattern. This time we have to analyze and dissect it a little bit closer in order to come up with what the probable solutions might be. Let's take a look at this next one. So again, by looking at this, can we predict or come up with a pattern that we see happening? So, well, we notice going here to here, it's kind of doing something similar to the last one. That would be times 2. But 4 to 5, that's not times 2. That does follow the times 2. This doesn't, but this does, so times 2. And this doesn't, but this probably does. So if that's the case, then the next number according to this should be 54. And since it followed that pattern for all of these other digits leading up to it, or all these other values leading up to it, it's safe to assume that that's going to be 54. Now let's take a look at the pattern at the bottom to see if we can figure out how to come up with this last example. So 2 to 4 is times 2, but to get to this next one, I'd have to add 1. There's nothing I can multiply or no multiplication that works with the 2 and the 4 with respect to the 5. And then I notice here it's not plus 1, which is what I thought would happen. This time it's plus 2. And then when I go here to here, this time it's plus 3. So based on this, I would think that this next one is probably plus 5. Sorry, plus 4. So it's going plus 1, plus 2, plus 3, plus 4. So our last value here would be 58. And now with all of these that we just went through and looked at, what I want you to think of or consider is the different ways. Like this is one way that I'm showing you of going through this, but there's always multiple ways that you can arrive at the answer. So go through and see, are there other ways of doing this or other patterns that you notice? Because it certainly isn't the only way to do this. Okay, then we have something like this that's kind of a review from what we did in chapter 4. We actually saw similar types of diagrams, and we talked about something called the figure number, and we called it n. So I'm going to write the n there, or the figure number, and this is the first figure number, second, third, fourth, ... and we would be looking for the 100th figure number. Okay, so then it's saying find the number of line segments. So let's count up how many line segments, I'm going to just call them line segments here, do we have in the first example. So if we take a look at it, we have 1, 2, 3, 4, 5, 6. So I have 6 there. When I look at that 6, I add these to it, 1, 2, 3, 4, 5. So I have 11 there. And then on to my next one, if we count that, we get 16. And here we get 21. And we're trying to figure out what it's going to be down here. So the only difference between this and the last one is that this time the numbers weren't given to us. We had diagrams given to us, and we had to use that to come up with these numbers or these values. But we're still using the same approach. So we want to look at the pattern or the relationship between the line segments. So what happens here to here? That's plus 5. That's also plus 5. That's also plus 5. So this is looking like the linear equations or the linear patterns we did in chapter 4. And to remind you, if you have the same number here each time, we call that the common difference. And we take that common difference and we always multiply it by our figure number. That's the first step in our equation. And then I'm going to put some dots here because it might just be 5n for my formula, or maybe I need to add or subtract something in order to come up with the pattern for this. So let's figure out if anything goes there where the dots are by testing it out with the first diagram here. In the first diagram, my n value is 1. 5 times 1 would give me an answer of 5, but I actually have a 6 here. So in order to get to 6, I'd have to add 1. So I'm thinking my pattern or my equation might be 5n plus 1, but I need to test it, so I'm going to try that with the second figure. In the second figure, I would have 5 times 2. That would give me 10, but my answer here is at 11. So yes, 5n plus 1 works because it worked for the first one, worked for the second one. So based on that, I can say in the 100th figure, I'd have 5 times 100 plus 1. So I would have 5, well, I guess I can just write it right here. 500 here plus 1, so 501 line segments in the 100th figure. Okay, so I hope that that is helpful and that it makes sense. This is an example of a linear pattern where the common difference, that pink part, is the same each time, which makes life easier for us. And then we'll come across some that don't have a linear pattern and they look a little bit different. So kind of like this example here. We can use a similar approach. So we do again want to use our figure number. So that's going to be 1, 2, 3, and then we're eventually looking for the 100th one. That's what it's asking for here. And this time we're looking for the number of squares. So I am going to draw just the number of squares here, and then we'll fill this in kind of like we're doing a chart. So here we'd have 2, here we'd have 2, 4, 6, and here we'd have 3, 6, 9, 12. So we're using this to try to see what the pattern is or if there's any sort of relationship here. So let's use this to try to see, is there a pattern? I could even draw it actually like a chart, like I could go like that. I find that charts are a great way for us to organize our information to help us to think clearly to figure this out. So do use that as a tool if you find it helpful. And so let's take a look. For the first number of squares, I have 2 of them. When I go up here, it doesn't really look like it's like the last example. So this would be plus 4, but then this one is plus 6. So I know it's not a linear pattern because they're going up by different values each time. I would think the next one is plus 8. We could draw it out to check, but we're not sure at this point. So we can look for other methods. If your pattern is not linear, then I think to myself, okay, if it's not linear, I'm probably multiplying two things together in order to come up with this. So I would think to myself, okay, I'm looking at these values here. What times what gives me these values? So this would be 1 times 2, it's a prime number. This would be 2 times 3, and this would be 3 times 4. Another way of looking at that is I noticed when I was doing this that I have maybe a better way for me to write this is notice that there's a relationship between the number of squares that are vertical. So that's 1, that's 2, and that's 3. And then notice the relationship with the other side. This side is actually 1 plus 1, so it's 2. 2 plus 1, so it's 3. 3 plus 1, so it's 4. So if I think about it, what's the relationship between the figure number and what we see going on there? Well, I could say that it is n times n plus 1. Does that work? Well, in the first one, that'd be 1 times 2. In the second one, that'd be 2 times 3. So yeah, that pattern works. So therefore, I would have 100 times 100 plus 1 for this last column. And so when I multiply that out, I end up getting 10,100 for our answer. So we can fill that in here, 10,100 in our 100th figure would be the answer. Your assignment is numbers 1 to 5 all. I hope you found this helpful and useful.